Sometimes the target vector is highly imbalanced, which means, for example, we have 90% of zeros and 10% of ones in your data set. Or there are more extreme cases, especially in the insurance industry. The probability of ones probably is just 0.1% and zero is 99.9%. So highly imbalanced data. In this case, it creates a lot of difficulties in fitting a machine learning model and to have a high quality prediction. So especially for the smaller class, right? For the, for example, 0.1% class, it's very difficult to make good predictions because the sample is too small. Okay, it's too small. And how to manage this situation on highly imbalanced classes, right? There are a few strategies. The first one is to collect more data. So if it is possible, we can collect more observations for the smaller class. But unfortunately, it might not be feasible in practice always. And the second strategy is to change the metrics used to evaluate your model. So we do nothing about the data, but we consider more metrics when we assess the model. So why do we need to change the metric? For classification problems, the most commonly used metric to evaluate this kind of model is the accuracy. And the probability of making a correct prediction, accuracy. However, if the data is highly imbalanced, for example, there are only 0.5% of observations have some rare cancer, and 99.5% of patients don't have the cancer, right? Which is very, very intuitive, right? Because it is a rare cancer. Right? In this case, even a very naive model can have a 99.5% accuracy. Why? Because you can just make a model like this. Okay? Given any new observation, predict that the person does not have the cancer, has that type of cancer. Then 99.5% of chances you are correct, because in the population only this many are healthy, they don't have that cancer. Okay? So accuracy won't work. It won't be a good metric to evaluate the model. Right? So in this case, we should consider some other metrics that can evaluate your model in a more comprehensive way. For example, you can create a confusion matrix or calculate precision, recall, F1 scores, etc. Okay, so and also ROC curves. So they can help us to evaluate the accuracy in the small classes in a more effective way and more precise way. Okay. And the third option is to use the class weighing parameters included in some models. Right? Some models have this argument, class weight, this parameter. You can set it to be true, to be equal to balanced. Then in the process of model fitting, they will try to increase the weight of the smaller class and decrease the weight of the larger class, okay, so that the result will be more balanced. Okay. And the last two strategies are downsampling the larger class or upsampling the smaller class. So these are kind of manual ways to handle this imbalanced class situation. So let's take a look at downsampling. So in downsampling, we create a random subset of the majority class of equal size to the minority class. So for example, we have, for example, we have 100 observations of 0 and only like 10 observations of 1. Okay. So in downsampling, we will draw a random sample of size 10 from the larger class. Okay. And then combine these two together to have a perfectly balanced data set and then fit the machine learning model. So this is called downsampling. Of course, this is not a good idea because we will waste a lot of observations in the larger class. Right? We shrink the sample size, which is in general not a good idea. And upsampling, the opposite. Right? So again, we have 100 zeros and 10 ones. Right? In this case, we will do resampling of the smaller class with replacement, and so that the sample size is equal to the larger class. Resampling. So in this case, we must allow replacement, right, so that we can essentially enlarge the size. But pay attention, the variation won't be changed, right? So, so this is another way. And there are some examples. There is one example about it. So let's finish this part. We will use the iris data set. So this one contains 3 balanced classes of 50 observations. So 3 classes, each one has 50 observations in the iris data set. Three classes, completely balanced. And we will manipulate the data a little bit. We will get rid of the first 40 observations for class 1, the first class. So then consequently, we only have 10 observations for the first class. And we also will combine the second and the third class together so that we have 100 observations in the second class and code it to 1. And this is 0. Originally, these are 0, 1, and 2. Right? We combine them together to get 1. Right? So that we create a imbalanced data set. Right? So this is what we do here. Right? So see, we import the iris data set and load the features matrix and target vector. And then we subset the features matrix and target vector, right, by starting the index from 40 and then to the end of the data set. And so basically we got rid of the first 40 observations. Right? And then we recode the target vector. You see, we use a where function. So if target is equal to 0, then 0, otherwise 1. So namely, we combine the second and third classes to 1, right? So that it's a binary problem after this step. Okay. And then I see how to do, let's skip this, how to do downsampling. Right? So we first save the indexes of zeros and ones in I class 0 and I class 1. Right, so you see, we use this conditional to select the indexes of these observations, these target observations. Right? So I class 0 basically are integers like 1, 0, 1, 2, 9. Okay, actually, and I class 1 will be what? Will be 10, 11, all the way to 109. Yeah, so totally 100 indexes for class 1 and 10 indexes for class 0. And then measure their length N class 0 will be 10, N class 1 will be 100. Okay. And then we use this random choice function to select 10 indexes from I class 1. Okay, so basically, select 10 numbers from this set. Okay, replacement equals false because we are doing downsampling. Okay, we are sampling 10 from 100 indexes, so we don't allow replacement. Okay. Then save it in here, I class 1 downsampled. So this set contains the indexes uh, that we will that for the downsampled class 1. Okay, downsample class 1. And then we can use them to choose observations for class 1 target values, right? And combine them with class 0, original class 0. So 10 plus 10, so now 20 indexes. Right? And next, we can use them to select features, the rows in the features matrix, and then combine them together. Oops, sorry, I forgot to run the previous code. So see the indexes, the target values for the new data set. It's completely balanced now. And also then, so we vertically stack the features matrix for the class 0 features and class 1 features. Right? So these are the first 5 rows. Right? So this is downsampling. Upsampling works similarly, but so now we will choose from I class 0. I class 0 is what? Is the small set 0, 1, all the way to 9. Okay. Right. So size is equal to n class 1. N class 1 is equal to 100, remember? So we will sample 100 indexes from this small set of 10 indexes. Of course, we need to let replace equals true. Okay, so this is called resampling. Okay, so we manually increase the size. Okay, and then we can, so you see, after we do it, so this is the target, the new target vector, 100 zeros and 100 ones now. Okay, because we resampled, yeah, 10 times. Okay. And similarly, we can vertically stack the 0 class, the new 0 class features and the 1 class features. So now the features matrix will have 200 rows. Originally only have 110 rows to 200 rows. We enlarge the smaller class. All right, perfect. I think we can stop here.